As reported by the Linux Foundation's 10th Annual Open Source Jobs Report, 77% of organizations are growing their use of cloud or container technologies. My name is Mumshad Manambeth, and this is the Kubernetes for the Absolute Beginners course. Kubernetes is the go-to platform for hosting production-grade applications. Currently, demand for engineers with knowledge on Kubernetes is on the rise, and it is the right time to start your Kubernetes journey. However, beginners often find it quite complex to start their Kubernetes journey, and this is mostly due to not having the right foundations or access to the right infrastructure to learn. Which is why in this course, we make sure we start with the basics and get your foundations in containers right before jumping into Kubernetes concepts. And we use illustrations combined with fun analogies to break down and simplify complex concepts. We also have demos that walk you through the basic concepts and show you how to do it yourself. But that's not all. The more fun stuff is in our hands-on labs. We have coding exercises where you will practice solving Kubernetes coding challenges in a live Kubernetes environment right in your browser. Yes, you don't have to have a high-end system or access to cloud platforms or worry about cloud costs to gain practice. We will provide you access to actual lab environments and challenges to practice on. Our labs are unique, as in we don't provide a blank environment and give you instructions to copy and paste. Instead, every lab is created specifically for the topic you just learned, and you're asked questions to explore and identify information in the lab or do specific tasks. And your job is to figure out how to do those tasks. So we will validate your work and give you feedback instantly. In case you're stuck, we have hints and solutions to help you. And if you're still stuck, we have a thriving community, and you get access to an exclusive Slack channel where you can interact with me and other students in the community and get your doubts cleared. We're also a CNCF certified Kubernetes training partner, so you can rest assured that you are in safe hands. We're so sure you'll benefit from our course that we offer a 30-day money-back guarantee, so there's nothing for you to lose. So jump right in, enroll today, and I'll see you in class. Hello, and welcome to this lecture on Kubernetes overview. In this lecture, we will go through an overview of Kubernetes. Kubernetes, also known as K8s, was built by Google based on their experience running containers in production. It is now an open source project and is arguably one of the best and most popular container orchestration technologies out there. In this lecture, we will try to understand Kubernetes at a high level. To understand Kubernetes, we must first understand two things: container and orchestration. Once we get familiarized with both of these terms, we would be in a position to understand what Kubernetes is capable of. We will start by looking at each of these next. We're now going to look at what containers are. Specifically, we will look at the most popular container technology out there, that is Docker. If you are familiar with Docker already, feel free to skip this lecture and move over to the next. Hello and welcome to this lecture on Docker overview. My name is Mumshad Manambeth and we are learning Docker fundamentals. In this lecture, we're going to look at a high-level overview on why you need Docker and what it can do for you. Let me start by sharing how I got introduced to Docker. In one of my previous projects, I had this requirement to set up an end-to-end stack, including various different technologies, like a web server using Node.js, a database such as MongoDB, a messaging system like Redis, and an orchestration tool like Ansible. We had a lot of issues developing this application with all these different components. First, their compatibility with the underlying operating system. We had to ensure that all these different services were compatible with the version of the operating system we were planning to use. There have been times when certain versions of these services were not compatible with the OS, and we've had to go back and look for another OS that was compatible with all these different services.
Secondly, we had to check the compatibility between these services and the libraries and dependencies on the OS. We've had issues where one service requires one version of a dependent library, whereas another service required another version. The architecture of our application changed over time. We've had to upgrade to newer versions of these components or change the database, etc. And every time something changed, we had to go through the same process of checking compatibility between these various components and the underlying infrastructure. This compatibility matrix issue is usually referred to as the matrix from hell. Next, every time we had a new developer on board, we found it really difficult to set up a new environment. The new developers had to follow a large set of instructions and run hundreds of commands to finally set up their environments. They had to make sure they were using the right operating system, the right versions of each of these components, and each developer had to set all that up by himself each time. We also had different development, test, and production environments. One developer may be comfortable using one OS and the others may be using another one. And so we couldn't guarantee that the application that we were building would run the same way in different environments. And so all of this made our life in developing, building, and shipping the application really difficult. So I needed something that could help us with the compatibility issue. Something that would allow us to modify or change these components without affecting the other components and even modify the underlying operating system as required. And that search landed me on Docker. With Docker, I was able to run each component in a separate container with its own libraries and its own dependencies, all on the same VM and the OS, but within separate environments or containers. We just had to build the Docker configuration once, and all our developers could now get started with a simple Docker run command. Irrespective of what the underlying operating system they run, all they needed to do was to make sure they had Docker installed on their systems. So what are containers? Containers are completely isolated environments, as in they can have their own processes or services, their own networking interfaces, their own mounts, just like virtual machines, except they all share the same operating system kernel. We will look at what that means in a bit. But it's also important to note that containers are not new with Docker. Containers have existed for about 10 years now, and some of the different types of containers are LXC, LXD, LXCFS, etc. Docker utilizes LXC containers. Setting up these container environments is hard as they are very low level, and that is where Docker offers a high-level tool with several powerful functions, making it really easy for end users like us. To understand how Docker works, let us revisit some basic concepts of operating systems first. If you look at operating systems like Ubuntu, Fedora, SUSE, or CentOS, they all consist of two things: an OS kernel and a set of software. The operating system kernel is responsible for interacting with the underlying hardware. While the OS kernel remains the same, which is Linux in this case, it's the software above it that makes these operating systems different. This software may consist of a different user interface, drivers, compilers, file managers, developer tools, etc. So you have a common Linux kernel shared across all operating systems and some custom software that differentiates operating systems from each other. We said earlier that Docker containers share the underlying kernel. What does that actually mean, sharing the kernel? Let's say we have a system with an Ubuntu OS with Docker installed on it. Docker can run any flavor of OS on top of it as long as they are all based on the same kernel, in this case Linux. If the underlying operating system is Ubuntu, Docker can run a container based on another distribution like Debian, Fedora, SUSE, or CentOS. Each Docker container only has the additional software that we just talked about in the previous slide that makes these operating systems different, and Docker utilizes the underlying kernel of Docker host, which works with all the operating systems above. So what is an OS that do not share the same kernel as these? Windows. And so you won't be able to run a Windows-based container on a Docker host with Linux OS on it. For that, you would require Docker on a Windows server. You might ask, isn't that a disadvantage then? Not being able to run another kernel on the OS? The answer is no, because unlike hypervisors, Docker is not meant to virtualize and run different operating systems and kernels on the same hardware. The main purpose of Docker is to containerize applications and to ship them and run them. So that brings us to the differences between virtual machines and containers, something that we tend to do, especially those from a virtualization background. As you can see on the right, in case of Docker, we have the underlying hardware infrastructure, then the operating system, and Docker installed on the OS. Docker can then manage the containers that run with libraries and dependencies alone. In case of a virtual machine, we have the OS on the underlying hardware, then the hypervisor like a ESX or virtualization of some kind, and then the virtual machines. As you can see, each virtual machine has its own operating system inside it, then the dependencies, and then the application. This overhead causes higher utilization of underlying resources as there are multiple virtual operating systems and kernels running. The virtual machines also consume higher disk space as each VM is heavy and is usually in gigabytes in size, whereas Docker containers are lightweight and are usually in megabytes in size. This allows Docker containers to boot up faster, usually in a matter of seconds, whereas virtual machines, as we know, takes minutes to boot up as it needs to boot up the entire operating system. It is also important to note that Docker has less isolation as more resources are shared between containers like the kernel, whereas VMs have complete isolation from each other. Since VMs don't rely on the underlying operating system or kernel, you can have different types of operating systems such as Linux-based or Windows-based on the same hypervisor, whereas it is not possible on a single Docker host. So these are some differences between the two. So how is it done? There are a lot of containerized versions of applications readily available as of today. So most organizations have their products containerized and available in a public Docker registry called Docker Hub or Docker Store already. For example, you can find images of most common operating systems, databases, and other services and tools. Once you identify the images you need and you install Docker on your host, bringing up an application stack is as easy as running a Docker run command with the name of the image. In this case, running a Docker run Ansible command will run an instance of Ansible on the Docker host. Similarly, run an instance of MongoDB, Redis, and Node.js using the Docker run command. When you run Node.js, just point to the location of the code repository on the host. If you need to run multiple instances of the web service, simply add as many instances as you need and configure a load balancer of some kind in the front. In case one of the instances was to fail, simply destroy that instance and launch a new instance. There are other solutions available for handling such cases that we will look at later during this course. We've been talking about images and containers. Let's understand the difference between the two. An image is a package or a template, just like a VM template that you might have worked with in the virtualization world. It is used to create one or more containers. Containers are running instances of images that are isolated and have their own environments and set of processes. As we have seen before, a lot of products have been Dockerized already. In case you cannot find what you're looking for, you could create an image yourself and push it to the Docker Hub repository, making it available for the public.
If you look at it, traditionally, developers developed applications.
Then they hand it over to ops team to deploy and manage it in production environments. They do that by providing a set of instructions, such as information about how the host must be set up, what prerequisites are to be installed on the host, and how the dependencies are to be configured, etc. The ops team uses this guide to set up the application. Since the ops team did not develop the application on their own, they struggle with setting it up. When they hit an issue, they work with the developers to resolve it. With Docker, a major portion of work involved in setting up the infrastructure is now in the hands of the developers in the form of a Docker file. The guide that the developers built previously to set up the infrastructure can now easily be put together into a Docker file to create an image for the applications. This image can now run on any container platform and is guaranteed to run the same way everywhere. So the ops team now can simply use the image to deploy the application. Since the image was already working when the developer built it and operations are not modifying it, it continues to work the same way when deployed in production. To learn more about containers, check out my other courses, Docker for the Absolute Beginners and Docker Swarm, where you can learn and practice Docker commands and create Docker files. That's the end of this lecture on containers and Docker. See you in the next lecture. Hello and welcome to this lecture on container orchestration. So we learned about containers and we now have our application packaged into a Docker container. But what's next? How do you run it in production? What if your application relies on other containers such as databases or messaging services or other backend services? What if the number of users increase and you need to scale your application? How do you scale down when the load decreases? To enable these functionalities, you need an underlying platform with a set of resources and capabilities. The platform needs to orchestrate the connectivity between the containers and automatically scale up or down based on the load. This whole process of automatically deploying and managing containers is known as container orchestration. Kubernetes is thus a container orchestration technology. There are multiple such technologies available today. Docker has its own tool called Docker Swarm, Kubernetes from Google, and MesOS from Apache. While Docker Swarm is really easy to set up and get started, it lacks some of the advanced features required for complex applications. MesOS, on the other hand, is quite difficult to set up and get started, but supports many advanced features. Kubernetes, arguably the most popular of it all, is a bit difficult to set up and get started, but provides a lot of options to customize deployments and supports deployment of complex architectures. Kubernetes is now supported on all public cloud service providers like GCP, Azure, and AWS, and the Kubernetes project is one of the top-ranked projects in GitHub. There are various advantages of container orchestration. Your application is now highly available as hardware failures do not bring your application down because you have multiple instances of your application running on different nodes. The user traffic is load balanced across the various containers. When demand increases, deploy more instances of the application seamlessly and within a matter of seconds. And we have the ability to do that at a service level. When we run out of hardware resources, scale the number of underlying nodes up or down without having to take down the application. And do all of these easily with a set of declarative object configuration files. And that is Kubernetes. It is a container orchestration technology used to orchestrate the deployment and management of hundreds and thousands of containers in a clustered environment. Don't worry if you didn't get all of what I just said. In the upcoming lectures, we will take a deeper look at the architecture and various concepts surrounding Kubernetes. That is all for this lecture. Thank you for listening, and I will see you in the next lecture.
Hello and welcome to this lecture. Before we head into setting up a Kubernetes cluster, it is important to understand some of the basic concepts. This is to make sense of the terms that we will come across while setting up a Kubernetes cluster. Let us start with nodes. A node is a machine, physical or virtual, on which Kubernetes is installed. A node is a worker machine, and that is where containers will be launched by Kubernetes. It was also known as minions in the past, so you might hear these terms used interchangeably. But what if the node on which your application is running fails? Well, obviously, our application goes down. So you need to have more than one node. A cluster is a set of nodes grouped together. This way, even if one node fails, you have your application still accessible from the other nodes. Moreover, having multiple nodes helps in sharing load as well. Now we have a cluster, but who is responsible for managing the cluster? Where is the information about the members of the cluster stored? How are the nodes monitored? When a node fails, how do you move the workload of the failed node to another worker node? That's where the master comes in. The master is another node with Kubernetes installed in it and is configured as a master. The master watches over the nodes in the cluster and is responsible for the actual orchestration of containers on the worker nodes. When you install Kubernetes on a system, you're actually installing the following components: an API server, an etcd service, a kubelet service, a container runtime, controllers, and schedulers. The API server acts as the front end for Kubernetes. The users, management devices, command line interfaces all talk to the API server to interact with the Kubernetes cluster. Next is the etcd key store. etcd is a distributed, reliable key value store used by Kubernetes to store all data used to manage the cluster. Think of it this way. When you have multiple nodes and multiple masters in your cluster, etcd stores all that information on all the nodes in the cluster in a distributed manner. etcd is responsible for implementing logs within the cluster to ensure that there are no conflicts between the masters. The scheduler is responsible for distributing work or containers across multiple nodes. It looks for newly created containers and assigns them to nodes. The controllers are the brain behind orchestration. They're responsible for noticing and responding when nodes, containers, or endpoints goes down. The controllers make decisions to bring up new containers in such cases. The container runtime is the underlying software that is used to run containers. In our case, it happens to be Docker, but there are other options as well. And finally, kubelet is the agent that runs on each node in the cluster. The agent is responsible for making sure that the containers are running on the nodes as expected. So far, we saw two types of servers, master and worker, and a set of components that make up Kubernetes. But how are these components distributed across different types of servers? In other words, how does one server become a master and the other the slave? The worker node, or minion as it is also known, is where the containers are hosted. For example, Docker containers. And to run Docker containers on a system, we need container runtime installed. And that's where the container runtime falls. In this case, it happens to be Docker. This doesn't have to be Docker. There are other container runtime alternatives available, such as Rocket or Cryo. But throughout this course, we are going to use Docker as our container runtime engine. The master server has the Kube API server, and that is what makes it a master. Similarly, the worker nodes have the kubelet agent that is responsible for interacting with the master to provide health information of the worker node and carry out actions requested by the master on the worker nodes. All the information gathered are stored in a key value store on the master. The key value store is based on the popular etcd framework as we just discussed. The master also has the control manager and the scheduler. There are other components as well, but we will stop there for now. The reason we went through this is to understand what components constitute the master and worker nodes. This will help us install and configure the right components on different systems when we set up our infrastructure. And finally, we also need to learn a little bit about one of the command line utilities known as the kube command line tool, or kubectl, or kube control as it is also called. The kube control tool is used to deploy and manage applications on a Kubernetes cluster, to get cluster information, to get the status of other nodes in the cluster, and to manage many other things. The kubectl run command is used to deploy an application on the cluster. The kubectl cluster info command is used to view information about the cluster, and the kubectl get nodes command is used to list all the nodes part of the cluster. That's all we need to know for now, and we will keep learning more commands throughout this course. We will explore more commands with kubectl when we learn the associated concepts. For now, just remember the run, cluster info, and get nodes commands, and that will help us get through the first few labs. That's it for this lecture. I will see you in the next lecture. Hey, so here is a quick reminder, and I hope you don't mind me jumping in like this. I wanted to take a moment to remind you about the importance of staying focused on the labs and videos that are provided in this course. Now, I understand that you may be eager to create your own local setup to practice, but I recommend that you resist that urge until you have completed the course. Our labs and videos are designed to give you a seamless learning experience that will help you gain the most out of the course in the time that you have available. By sticking to the labs and videos provided in the course, you can minimize distractions and interruptions and ensure that you have a clear path from start to finish. And this will help you stay focused on your learning goals and make the most of your time with us. Rest assured, we will provide you with resources to create your own local setup at the appropriate time in the course. For now, let's focus on the labs so you can gain the knowledge and skills you need to succeed. Thank you for choosing our course, thank you for choosing Code Cloud, and we look forward to helping you achieve your learning goals.